we will be presenting our paper Cheating Depth, Enhancing 3D Surface Anomaly Detection via Depth Simulation. In the standard anomaly detection problem setup, only anomaly-free images are available during training. The goal of the trained anomaly detection model is to learn the anomaly-free appearance of the object and detect any anomalous appearance deviations at test time. A wide variety of methods have been proposed to tackle anomaly detection in RGB images. However, some anomalies can be difficult to detect in RGB and require additional depth information. Simply applying RGB anomaly detection methods to 3D anomaly detection can be challenging since many top-performing anomaly detection methods require large pre-trained backbones which are simply not available for the industrial depth domain. Efficient large backbones are also difficult to train due to the lack of the domain-specific datasets. Some discriminative anomaly detection methods are trained on simulated anomalies and require only a simple patch representation for a given domain, which can be learned by a vector quantized autoencoder. This representation can be learned from simulated data. Our contributions are therefore as follows. A novel depth-aware discrete autoencoder model is proposed, which is trained on simulated depth data that learns the representation necessary for anomaly detection. Additionally, 3DSR, a discriminative anomaly detection method, is proposed that is trained using simulated anomalies sampled from the discrete representation learned from simulated depth data, leading to an accurate 3D anomaly detection model. The proposed approach requires no large external depth dataset. The 3DSR method is trained only on anomaly-free RGB and depth pairs without requiring a large pre-trained backbone. The training of 3DSR is performed in two stages. First, the Depth-Aware Discrete Autoencoder is trained. Its architecture is based on the vector quantized autoencoder. However, in order to separate the parameters of the RGB and depth representation, grouped convolution is used both in the encoder and the decoder. The autoencoder is then trained on pairs of ImageNet RGB images and simulated depth images. The trained autoencoder outputs high-fidelity reconstructions of the input RGB and depth pairs. In the second stage, the 3DSR model is trained. The input image is first projected to the latent space by the depth-aware encoder. Then, simulated anomalies are generated at feature level by replacing the feature vectors with random vectors from the learned codebooks. This process is capable of producing a diverse set of anomalies. The object-specific decoder is trained to reconstruct anomaly-free appearance from the features corrupted by simulated anomalies. The general object decoder reconstructs even anomalous appearance. The anomaly detection module then utilizes the information from both the anomalous and the anomaly-free reconstructions to output an anomaly segmentation mask. 3DSR achieves state-of-the-art anomaly detection results both in the 3D setup where only the depth information is available, as well as the 3D and RGB setup where both modalities are available. For more details, please see our paper.